Okay, we're picking up where we left off. This is Algebra 2 notes, section 5.4, and this is page 6. All right, we briefly discussed perfect square trinomials on the last page, and what we're going to do here is show you how to recognize them. What you want to look for is a positive perfect square on each end of the expression. It'll be a trinomial expression. Sorry, let me spell that correctly. Perfect square on each end. And we'll cover the second condition in a minute here. But it's going to be that the middle term is either twice the product of the square roots of the ends or the opposite of that. So positive or negative, okay? So we'll cover that part of it in a minute here. But let's look for positive perfect squares on each end. That would be 4 times 4, and we have a positive. This is 3x times 3x. This one here is 6x times 6x, and this one's 7 times 7. This one here is 25. X squared would be 5x times 5x, and this one would be 1 times 1. So if you look on the other one here, we have a number down there that is not a perfect square. And even though this one is, the front one would be 2x times 2x. This next example here, we have a negative number, and perfect squares are positive. So that one won't work. Now, the next here is a little different. It's got a perfect square on each of these. So we have to reject that one for a different reason. Okay, so I'm going to show you what the second condition is. The middle term has to either be the positive version or the negative version of the square roots multiplied together. So let me kind of show you on this first example. 3x, and that would be the square root of that one, and 4 would be the square root of that one. When you multiply those, you get 12x. You double that, you get 24x, and we can either have in the middle the 24x or its opposite. So this one's good. Okay. This is 6x. Oops, let me write it correctly. 6x, and this would be 7 times 7, the 49. Multiply, you get 42. Double that, you get 84. So that one's good. This would be 5x. This last one is 1 times 1. When you multiply them, you get 5x. And double it, you get 10x. We can either have the exact value, 10x, or the opposite of that. So when we come over here, you're going to see the middle term is the problem. This is 2n times 2n. The back is 5 times 5. When you multiply those two expressions, 2n times 5, you get 10n. Doubling that would give 20n, and this is the wrong value here. So these all fail for different reasons. Okay, so now I'm going to explain that a GCF can sometimes disguise them. So in example 26, if I pull the 5 that's your greatest common factor out of this, you get 9x squared minus 6x plus 1. You could distribute there to check my work. So the square root, you got a positive perfect square on each end now. And the square root here is 3x, and the back one is 1 times 1. Multiplying those gives 3x, doubled is 6x. So this is good, and now I just have to show you how to actually factor these. So here's how you do it. All right, you look for a GCF first. Often I use those to disguise these problems. Keep it as part of your answer, don't lose it. Then you simply use the square roots. Sorry, let me write this correctly. The square roots of the ends and the sine of the middle. And you can finally rewrite your answer as a perfect square. All right, so this one doesn't look like it's the right type until you take the common factor of 3 out of it. And you get 4x squared minus 20x plus 25. Now the red flag here that tells you you're probably dealing with one is this is a positive perfect square, and so is that. And if you take the square roots, you get 2x and 5. When you multiply it, you get 10x. Doubled gives 20. So this is the right type. Okay, so what you're going to do now is you're going to keep that common factor there. That's part of your answer. Take the square roots of each end. So 4x would be 2x times 2x. And the 25 would be 5 times 5. And then you simply borrow the sign of the middle one. And this can always be rewritten with an exponent instead, since we have actually matching values that are being multiplied by each other. Okay, so that does it for page 6. And page 7, I'll do a little bit more practice with this and finally give you the last style of factoring, which is called difference of squares. It'll look a little bit like this, but it has some uniqueness to it.